In the last lecture, a series of lectures, the previous cases, we discussed about different kinds of marine structures, varieties of marine structures, bottom founded or bottom supported, flexible systems, new generation structures where form governs the functional design of the marine structures. Subsequently, we discussed about the environmental loads acting on marine structures. We discussed in detail about the hydrodynamic loading coming on the marine structure. We also discussed about wind loads. We also discussed about seismic loads, earthquake loads, which is acting on the marine structures. So in this lecture, briefly we will again cover the remaining other loads on current, dead load, live load and impact loads which act on marine structures. Once we understand this, we will move on to the ultimate load design principles in this lecture. So let us talk about the effect of current or the influence of current as a load on marine structures. Current has actually three significant effects. On the structures. Let us say for example, the first could be current velocity should be added vectorially. With the water particle velocity, to be very specific I should say horizontal. To compute can you tell me where this horizontal water particle velocity plays a role in computing force on structures? You can compute the drag force. If you look at the Morrison's equation, which is applicable for slender structures, the drag force can be given by half rho CD diameter u minus x dot and u dot minus x dot. That is the drag component in the horizontal in the Morrison equation. Now where u dot is the water particle velocity horizontal, x dot of course the structural velocity horizontal. If you have the current value to be also included in my study, then I should say half rho CD dia u dot plus uc dot minus x dot of u dot plus uc dot minus x dot. So I should add the current vectorially, of course I say plus here, but it is vectorially to be added depending upon the value. So you can see from this equation, since the drag force is velocity square, you can see it's velocity square. So current has significant influence so that is the first part. How do we handle current as a force? The second could be presence of current changes wave celerity Therefore, the steepening of the wave elevation is affected. But studies have shown in the literature that effect of current on the wave celerity is very less. So generally it can be ignored. The third effect what the current has as a force on marine structure is current makes the structure to generate forces. So, this will cause what we call I should say additional diffraction forces. Because it will make the structure to generate forces. However, these forces in sense the diffraction force caused by the structure because of action of current on the structure, these forces are very less compared to the normal diffraction force. And generally this is neglected. So, these are the three consequences of current as you see as a force on marine structure, out of which the case 2 and case 3 is generally ignored in the literature, it is not important. The first one, why it is important? Because interestingly if you look at any structural member which may be floating or bottom supported, this becomes my still water level or mean sea level, you will see that the velocity variation, horizontal velocity variation is practically 0 as you increase the depth, whereas it is maximum near the mean sea level, okay, it is maximum. So, I should say that current decreases slowly with depth, okay. With the depth current decreases very slowly. Since u dot c is to be added vectorially to u dot in computing the drag force, which is velocity square term. Therefore, current influences drag component of the force significant. That is the summary what we have as far as the current force is concerned. So, let us quickly see what we have seen so far. Under the environmental loads acting on marine structures, we discussed about hydrodynamic loading, we started with a simple sea surface elevation given by classical linear wave theory given by Airy's. We all agree that why the wave theory is called linear, I already said this in the previous lecture. So, based on this we compute water particle kinematics if the structure is fixed or the structure is large diameter or the structure is slender or compliant, I use appropriate equation to compute the wave forces. Let us say for a compliant structure the wave force is computed using the Morrison equation, and now we know how to compute the wave force. We discussed about the wind force, that is the aerodynamic loading. Wind force has two components, one is the mean component, other is the gust component which is fluctuating. One will give you the static effect, other is giving you the variation with respect to time. So, wind generally caused wind induced vibration on structures. This will significantly influence wind induced vibration on flexible structures. So, how the dynamic component or how the gust component can be handled, because one is random process, how to handle this in a closed form solution. We have got aerodynamic admittance function which helps us to handle this issue easily in computing the wave forces. Now the question comes, what spectrum should I use for finding out the wave forces, because for for wave forces we already have Pearson-Moskowitz spectrum, modified Pearson-Moskowitz spectrum, John Swap, etc. Whereas when it comes for wind forces, people said I will use 1/7 power law, but that is generally used for fixed type structures. For flexible type structures there are different spectra given in the literature. One classical example which is commonly accepted for flexible type structures is the spectra suggested by API and so on, which we saw in the last. What are the factors on which this spectrum is dependent, etc. We have seen them. Thirdly, we also discussed about seismic loads, earthquake forces. Earthquake forces is predominantly affecting bottom supported structure because it can transfer the force from the seabed to the structure directly. This induces inertia component, it does not induce or initiate drag component in the structure, whereas wind and wave both induces drag component. In addition, wave induces inertia component also, whereas earthquake force induces only the inertia component. So, mass of the structure is very important, and we all understand offshore structures are very large in size and very heavy in mass or weight. Therefore, inertia forces become predominant. When they are bottom supported, it is directly superimposed, but does not mean that earthquake forces cannot influence structures which are taut mode. We picked up an example in the last lecture. We showed you how a taut mode system like a TLP can also be influenced by an earthquake force significantly by an indirect mechanism which is suggested by the various research in the literature. In this lecture we have started with introducing current forces. What is the effect of current force on marine structures? What are those three domains of contribution, out of which is important and why? Now we look into the conventional forces which are otherwise common to other kind of structures. For example, dead load. What would be the dead load in terms of its intensity, and what do you understand by dead load? A very clear, explicit, interesting and intelligent definitions are given for the dead load, live load, impact load in API RP. You must read these codes, the references are available in the NPTEL website of this course, but still I will reproduce them as a very brief summary here for our understanding. Okay. Dead load is essentially the weight of the structure in air this will include the following. Include the following means includes the weight of the following. Okay. Weight of the overall platform. You know how to compute this because you know the member dimension, you know the material, you know density, you know the volume, and therefore you can find the overall weight of the platform in air. Remember, we all understand that there is a difference between the weight of the platform in air and water. 2. Weight comes from the piling, weight comes from the superstructure, weight comes from the drilling, sorry, this is excluded, this is excluded. Jackets, stiffeners, piping, conduits, corrosion anodes, decking, grouts, railing, and other appurtenances. Appurtenances means fittings, fixtures or fittings. Now interestingly, we must understand which are excluded in the dead weight, that is very important. Included is all these, but there are very classical exclusion of the dead weight which you should not consider as a dead weight. What are they? They are very important to understand why are they excluded and where are they included. We must know this. See, interestingly, marine structures are form driven systems. They keep on changing the geometry, the profile, arrangement of members as the water depth keeps on increasing, as the function for deep water generation is keep on changing every day or maybe every season. Now we have moved from shallow waters of 20 meters of oil exploration to 2000 meters of oil exploration, the present standards. If you pick up any one specific case of an offshore structure which is meant for 1500 meters like a spar platform or a triceratop or a TBLP, tension buoyant like platforms, where we can go for deeper depths. Unless otherwise we understand very clearly the design mechanisms, what are the loads contributing to these members, we will not be able to proceed further for ultimate load design and plastic design, because they all will look for you as a mathematical equation and getting the solution from solving the problems, but where are the source of loads coming from you will never know. If you do not know the variety of loads coming on the structure, you will not appreciate what are the deficiencies in calculating these loads accurately. Therefore, the question of how your design mechanism is reliable is not understood. So, reliability part of advanced marine structures will not be understood by you. If you do not know where are the loads coming concentrated on the members, you cannot understand the stress concentration development in the third module, you will not agree or you will not realize how do you do the fatigue design. So, it is very important fundamentally, first let us understand what are different kinds of structures, what are the different kinds of loads. Probably you would have understood all these things in some other courses parallelly, but it is my responsibility for you to make it clear before we proceed further for ultimate load design, because I must understand where are the contributions coming in the format of load, in the format of strength on the members, because these are the two parameters where I will keep on handling for ultimate load design in the next few lectures. So, if you are not clear about the sources of the loads, where they are coming from, which are included, which are excluded, and what are the intensity values, approximate idea, okay, how much live load or dead load I must consider on a deck platform of 90 meter by 90 meter, I must have an idea, otherwise you will never really understand the problem in a physical meaning. Okay. So, there are some classical exclusions in dead loads. One, drilling equipment weight. Two, production or treatment equipment weight. 3, weight of drilling supplies. Weight of treatment supplies. Drilling load. Now, there are reasons why they are excluded. First, let us see what are excluded. What do you mean by drilling equipment weight? Let us see this. This is nothing but weight of drilling equipments used for drilling, which are placed on the derrick, which are placed on the deck. Example, derrick, drawworks. You understand what is a drawwork? Drawworks are those mechanical equipments which are used for drawing oil or sucking oil from the seabed. They are called drawworks in general. Mud pumps, we all know why mud pumps are required. Drilling mud is a very important component in drilling operation, and we need to pump these muds because they are a very high specific gravity, they do not flow automatically, we have got to pump them. So, mud pumps, etc. I should say etc. They are all excluded. Okay. Production treatment equipment includes, let us say, separators, compressors, jumbo heat treaters. These are all equipments which are required to process the oil what you get from the sea. Now, one may wonder, why should I process it? I am talking about a marine structure somewhere offshore, which is about, let us say, 100-200 kilometers away from the coast, somewhere in the middle of the sea where the water depth is about 1500 meters. I am looking for an oil exploration at a depth of about 1000 meters. My platform cost is very, very high, the service life is only 10 to 15 years. Why should I invest on treatment plants on the offshore system itself? Why can't I simply explore the oil and keep on transporting it to the onshore and do all these treatments onshore? There are two main reasons for this. One is the cost, because what you produce X volume of oil, all what you explore is not oil, you have got to process it to extrude oil from that. The majority will become a crude. So, if you are transporting the X volume completely from offshore to onshore, your cost of transportation for transporting the slug or the rubbish will be unnecessarily high. So, what people have thought in recent times is, let us process it in the plant itself in offshore and only transport the net worth of financial asset to onshore. Now, the concept of FSRU came into play, floating storage regasification units. So, it is floating system, it is having enormous storage, it does not do drilling. Remember, very importantly, it is not an FPSO or FSO. Okay. It is floating storage offloading, this is floating production storage and offloading. Okay. but these platforms, or at least this for sure, does drilling, whereas this only floats, of course it has got enough storage and offloads it to the tanker, whereas in this case they do floating storage, they do regasification, there is a process happening here. So this is a recent investment which has come now, maybe very recently within couple of years. So people are looking for a very large investment on FSRUs in the current standards, because treatment becomes expensive when you transport the slug to onshore. So these are some equipments which are used for etc. for treating the oil what you have explored. So these are all excluded from the classical dead load of a marine structure. If you look at the drilling supplies, they include weight which comes from the drilling mud, water, fuel, essentially it is diesel, etc. I should call them as variables. Okay. You do not know how much mud you will be stocking, how much water do you require, how much water you will depump, etc. These are all drilling supplies. If you talk about treatment supplies, fluid, separators, chemicals like emulsifiers, etc. What does it mean? These are all used in the treatment process in the units here, like drilling mud is used for drilling equipment. Similarly, these are all nothing but the variables used for treatment process in the plant. These are all excluded from the classical dead load of marine structures, we do not include them. Drilling load includes the derrick load, pipe storage, rotary table load, I should say etc. always, okay. There are many things which you are not mentioning here. So these are all excluded in the classical dead load, which we otherwise consider like including this. So essentially if you look at in summary, dead loads are related to weight of the structural system only. Variables are excluded, process equipments are excluded from the classical dead loads, okay. Now where do we consider them? Where do we include them in our load capacity? We will talk about that. So I have a small homework for you. You try to look into the literature, not necessarily API, RP, not the code. Look at the literature, try to find out approximately weight of each component in air, okay. So there are very many kind of platforms already installed. Look into the Wikipedia of every platform. There are certain books which has been advised to you in the literature, read them, you will find a tabular column giving weight of each component approximately in terms of the percentage of the overall weight, and the overall weight is of course given in the literature, okay. Try to give an idea, get an idea that how they are contributing to the overall weight, okay. Next of course will be the live load. These loads are in addition to the dead load which are applied statically, remember this, So, static component you may say live load will vary with time. For example, for buildings, just for understanding of the viewers, for example for buildings, when you design a building, let us take a component of a building, let us say a floor slab. IS 875, the loading code advises a live load of 2.5 kilonewton per square meter to 4 kilonewton per square meter depending upon the choice of the designer. What does it mean? In 1 square meter area you can use 2.5 kilonewton, that is 2.5 into 1000 by 10, which comes to 250 kg. It means if you apply or if you use a live load of 250 kg in 1 square meter, taking an average human weight as 80 or let us say 60 kg, you are approximately allowing 4 people to stand in one floor. On the other hand, if your drawing room is approximately a size of 3 meter by 3 meter, 9 square meter into 4 people, you have 36 persons living in your house only in the drawing room. Okay. Imagine the other rooms and imagine the total area. So, one can clearly understand this is a very highly conservative number. Okay. But in a building, in a floor slab, in a drawing room like this, all the load will not be acting continuously throughout the day, because the load pattern will shift from drawing room to kitchen to dining to bedroom to service areas, etc. For example, in an institution, in a school, classroom to library to restrooms to corridors to play areas, etc. There will be a shift depending upon the timing of operation. So, in real sense, if you see, live load should be time dependent. On Saturdays and Sundays, 0 live load. It should be period dependent also, etc. Isn't it? But remember, importantly, these factors are ignored, they are considered as independent of, they are statically applied. Okay. So, we obviously cannot handle the live load suggested by building codes onto offshore structures, because we have a different concept. It is also a structure, but our operational loads in terms of live load are different. So, in our case, where do the live loads come from? For example, in a house like this example, you have seen live loads come from human being, etc. But here we have only very limited number of people operating on the deck, isn't it? We have got maximum 50 to 75 people on board, which will work, whereas the area is 100 meters square, 100 meter by 100 meter. The TLP typically has a side of a square platform about 75 to 90 meters. So, 10,000 square meters, only 50 people live. So, live load cannot be simply based upon the load what you have from the human being. So, what are the sources of the live load coming on the structure in offshore or in marine structures? So, they include the impact loads arise from the operational equipments So, what is the guideline? How do I know? Because I have said simply operational equipments. I would also, these equipments have a rotary mechanism, because they are not static, they are running, they are working like a generator, like a heat exchanger. They have compressors, compressors have rotors, they will keep on operating. So, the operational speed will impose certain dynamic effects on the platform where they are installed. So, we have to have an impact load. What is the guidance advised by the codes? Interestingly, I must now look as a designer, instead of studying the concepts, let me look at the numbers. Okay. The typical live load, I should say factors, are the following. Let us say area, let us say uniform load on beams, make a column, let us say concentrated load on beams. So, let us say this is on decks, this is concentrated load on beams. First, let us try to understand the difference between these three before we write down the numbers in the area of description. Though you may be knowing it, but still, since this course does not have any prerequisite, the audience can be even from any source of mechanical, electrical, etc. Let us try to understand what do you understand by uniform load, concentrated load, beam, deck, etc. Let us say I have an offshore platform, maybe a TLP, maybe a jacket, not more. Now, I pick up only this and try to draw. I call this as a deck supporting system. So, the deck comprises of essentially a plate, I am just drawing only a line diagram, essentially a plate of x thickness, okay. But obviously, as the plate is very large, maybe 90 meter, you put any thickness here, the plate will start buckling, is it not? It will not bend, it will not take any load. So, I have got to put stiffeners. These stiffeners can be called as beams, they can be called as primary and secondary beams depending upon on what direction you are running, and they can be generally an I section, they can be a composite I section, they can be a face to face channel, they can be a back to back channel, they can be a back to back channel with a plate, all these are what we call built up sections, we call them as beams, we call this as deck. So, what we are saying here is uniform load on the beams and decks, that is load on this area. So, the intensity of this column should be so many load per square meter, that is called uniform load, is uniformly applied. Concentrated load on decks, these decks sometimes will have concentrated load also, sometimes you do not know, an equipment can be standing. For example, I have an equipment here which can be a compressor, it has got 4 columns on which it is resting. So, all these 4 columns will impose a concentrated load at the point where it is being resting on the deck, that is what we say as concentrated load. Sometimes unfortunately or fortunately these loads can also act exactly on the beam line also, we do not know. Can you give me an example where the beam line load can be developed? You have heard about moon pool. Moon pool is an opening given in the deck to perform drilling operation. The drilling derrick is a single standing equipment or a stack which cannot be re-erected every time, okay, because that takes a lot of time. What they do is, interestingly, if you look at the view here, I am drawing only one segment of this, they put a railing, this is a railing, both. And these are all slots, okay, they are removable slots, you can remove them if you want. You can remove the plate, it becomes a moon pool, okay. So, the derrick which will make to move on this, wherever you want to operate the drilling you can do that, okay. So, this becomes a rolling load which is also a concentrated load on these beams. Okay, that is what we are looking at here. Okay. So, let us look at the areas here. Can be walkways, staircase, etc. 4.79 kilonewton as expected, it is load intensity per area. This is 4.38 kilonewton per meter. This is 4.45 kilonewton. Now, if you have a deck whose area is larger than 40 square meters, you have a deck area which is larger than 40 square meter, then the load will be 3.11 kilonewton per square meter. Of course, since it is a deck, we are not talking about concentrated loads. If you have got areas of light use not used for process, maybe living quarters, for example living quarters, then in that case this becomes 11.9 kilonewton per square meter. You may wonder, interestingly, sir, we say area of light use, but the intensity is much more than we have got areas of operational use. Why it is so? I will explain that. This 10.95 kilonewton per meter, it is 267 kilonewton and so on. You have a reference for this. I wish to state the reference so that if you have made any mistake you can correct it. Graph Wj Introduction to Offshore Structures, Design, Fabrication and Erection. Gulf Publishing Company, Houston. Unfortunately, remember the year. I'll give you the year next class. I have forgotten to note down here. I'll give you this. So let us come back to this question of argument, that why area of light use will have large intensity compared to that of areas where you have got operational area of 40 square meters. Coming back to the functional use of any platform, as we saw here, areas of light use will be limited. The areas used for light use or meant for light use will be highly restricted. So, even though the intensity is larger, when you multiply with the area, the total load on the system because of this will become lower. Okay? Whereas the operational areas are very, very high. So, if we multiply this intensity with this area, unnecessarily the load on the structure will become very large. Example, building, live load 2.5 kilonewton per square meter, approximately saying 4 persons on 1 square meter area, which is unimaginable load, highly conservative. So, you must appreciate that when live loads were prepared for offshore platforms, there has been very intelligent thought of identifying the magnitude and intensity very carefully. So, there is no conservatism here. Okay. They are clear. Of course, this changes the designer's option, changes with of course what kind of equipment you are using, but it is only an idea just to know what is the value in comparison to the buildings. Okay. And you will now note very clearly all the values stated here are much higher than meant for buildings. Okay. Whereas I said 2.5 to 4, but this is 4.79, this is 3.11, this is 11.9. very high. Okay. So that is what we are talking about, the live load here. Now interesting factor, these live loads are considered static, but they essentially come from movement of equipments or vehicles or drilling derricks, etc. So there should be some impact on this. Why impact will be there? Because when any vehicle or any equipment operates or moves and applies a brake or changes its speed or alters its acceleration and velocity, it will cause an additional impact to the restraint offered by the support. Example, car is moving on a road at a velocity of let us say 60 km per hour, apply a brake, the vehicle stops. Now the reaction force which makes the vehicle to stop essentially comes from the friction between the tire and the surface on which it is running. So the reaction force is offered by the restraint boundary which is given to the car. Similar way here, when an equipment is operating, when you want to change the operational speed because of the requirements from the operational mechanism, those changes will all affect or get affected by the boundary on which it is restraining, nothing but the platform deck. So they all will be impact loads. Now the question is very difficult to find out what would be this impact load on an average operation of an equipment on a floating system like this. Okay. So people have said, let me multiply these live loads with a factor to create an impact load. So I am looking now for impact load factors. So impact load is not essentially arrived directly from any equipment, we simply pick up the live loads and multiply them with a specific number, what we call as IL factors, impact load factors. You may wonder, is it the practice commonly available in structures, in buildings? Yes, answer is bridges. If you look at IRC, Indian Road Congress 5, 6, 21, these are the numbers of IRC code. For example, they are all meant for design of railway and road bridges where moving loads are there, vehicles are travelling, where cranes are also operated, for example. All in these codes they say that the impact load caused by the vehicle movement will be enhanced by a multiplying factor on the live load. So this practice has been common in almost all codes which speak about impact loads. Okay. Similar concept is adopted in marine structures design also. So now I am talking about impact loads, but as I said, I am not talking about impact load directly, I am handling this indirectly. So impact loads, we all understand that any vibrating or rotary machinery will cause dynamic amplification which I call as impact. Therefore, live loads are multiplied by impact loads factor to get the corresponding effect of dynamic amplification. You understand this? Just to get the amplification of the dynamic effect on the members, we multiply the live loads with some impact factors. That is why I call this as impact factors on the live loads. Okay. Impact load factors. So again a table. So description. Load direction. The impact load cannot remain same for horizontal and vertical, okay, cannot remain same. So I should say horizontal and vertical. if we have a rated load on cranes, for horizontal the impact is 20%, for vertical it is 100%. This is for the crane loads, cranes. If you look for supports of the rotary or rotating machinery equipments, then the horizontal impact and vertical impact factors are equal. If you look at impact because of boat landing, then here it is a specific value given. In addition to this, what would be the common uniform distributed load which is advised on the decks? This is 11.975 Newton per square meter in the drilling area these are all original live loads. Okay. 71.85 Newton per square meter in the derrick area, 47.9 Newton per square meter in the pipe rack area. These are what we call as deck floor loads. These are all the loads which comes on the deck floor. So, with this lecture, ladies and gentlemen, we have completed the comprehensive summary of all the loads acting on marine structures. We have understood now what are the different kinds of loads, varieties of loads coming on marine structures, how are they handled in the analysis, which factors influencing what, how much, why, how are they designated in the literature, which are the different spectrums which are being appropriately used, what is the effect of these forces in combined nature on the marine structures, which is dynamic, which is static, which is deterministic, which is probabilistic, why, how are they handled, what are the different parallel functions which can map the probabilistic on a deterministic issue, which load can combine with what, why, what would be the effect, all we have seen in these 6-7 lectures along with the different varieties of marine structures we have studied. With this basis, we will move on to the next lecture, we will talk about ultimate load design principles and factors which will affect, then we will slowly move on to the plastic design of marine structures.